Good morning. Yesterday we did the exercises 117 and 118, and the 117 was a program that would print lines above a certain threshold. It was called threshold.c in this source code directory, and then 118 would be removing trailing blanks and trailing white space and any lines that only contain white space. And today we can go try and do 119. And yes, so reversing a string is actually way more complicated than it seems because of Unicode, especially with UTF-8. Reversing a string requires normalizing the string in a certain way, and when you have to reverse it grapheme by grapheme and not byte by byte, which is obscenely complicated. So for today's video, I'm going to assume we will only be dealing with US ASCII, otherwise we will have to spend another 40 hours just for this exercise. And thank you all for the amazing feedback I've been getting on the previous videos. I got like 5 comments, which by the standards of this channel is actually a lot. And I got myself a green screen, and I'm not yet really used to using it, so it may look weird. Also, it seems like I'm going to be hating the shape of my mouth while speaking. It's so weird. Okay, exercise 119, write a function reverse s that reverses the character string s. Use it to write a program that reverses its input a line at a time. Hang on. I opened a terminal on the wrong computer. Streaming, not this one. This one? Okay. And copy git ignore from 06 to 07, and then cd 07, and the make file. Okay, the reverse.c, and we include stdio, I guess, and we define a function. I'm not entirely sure how we're going to do it, because if we return a string, then we are going to have to define to also free it after each use. So, I mean, if we use a dynamically allocated string, we're going to have to free it after each use. So I think we can do it just like before. We just reverse. We're going to use it just like before. We allocate the strings beforehand, and then we just pass a pointer to it, to this reverse function. Oh, no, it never mentioned if we're going to have to reverse it in place. Okay, yeah, I'm going to assume it's going to be reversing a string in place. So void reverse, and this is going to be a char s like this, and then in int main we will think what we're going to be doing inside of here, and then void reverse. So we're going to need the string length. Equals string length of s. So easy. And what does string length return? Not very helpful. Okay. The string length function calculates the length of a string pointed to by s, excluding the terminating null byte 0. So we can probably assume that it's going to the last character is going to be a new line, and we are going to need some sort of what was it called? We're going to need some sort of loop. Okay, so int so for I equals 0, we're going to start from length. For I equals length, I is greater than or equal to 0. No, it means greater than 0. Greater than or equal to 0, right? I minus. So we are go from last to first character. Let's see. And we need to find out the corresponding so we're basically going to be or maybe no, probably we don't have to reverse it in place. We only need to go from back and just put the we only need to go from the back and return the characters one by one. Anyway, we know the length. I'm going to just return a new string instead. Char path equals malloc length of string plus 1, and return the buffer. And this means we are going to have to free this line after we don't use it anymore. Okay, and we can go from 0 to length, like so. Let's see. I'm not entirely sure how this is going to function, so I'm just thinking out loud. Uh, if see, okay, we can start from the end. So C equals S length minus I, like this. This is going to start with, okay, I think length, if we just pass the length, we're going to get the null terminator. So we have to start with 1. And I is less than or equal to length, like so. Then we go back down to 0. So C is the last character. And if C equals new line, if it's a new line, we no, probably we just don't have to do it like this. Okay, we just really reverse it no matter how you give it to me. So C equals S length of I buffer I minus 1 equals C. Like this. Does this make sense? And we can just try. So my char string equals hello world, and char reversed equals reverse s, printf s reversed, return 0, make reverse. Yeah, makes sense. So what if we wanted to return the, what if we wanted to reverse input? Then I guess we would need to use getLine. So char line equals null, size t length equals 0. Or size, we don't have to pass it, okay. And then while and size t length and number of red bytes, while n red equals get line line length and stdin is not -1. So for every line in the input, standard input, then Yeah, we could just. So we are kind of cheating because we are using modern C, and we could allocate a new line for every line. So let's try with this implement like this. Char okay, char pointer rev equals null. Char pointer okay, so reverse equals reverse okay, and if we are doing new line, then we want to truncate it. So if line of unread equals a new line, then we truncate the input. So unread equals S0 terminator. So this will just ignore the last the new line. So this, and since we are going to be allocating the a new buffer every time, we need to free. Okay, we print the string, the reverse line, and we free the reverse string, like so. Oh boy, let's see if this even works. Reverse.c. Okay, well, so what? For I equals, okay, return buffer. Wait, what? If -1 equals n, and how about this? Okay, yeah, that makes more sense. But why does this say xn? Wait, what? I have no idea what this says, so okay, I'm assuming this is some way in which the system is returning. I'm assuming this is somehow is what becomes of a tab in my case. I would have to see what this means in like, okay, it's 88. Okay, I have no idea why I get those n backtick x's in here. I'm assuming it could be somehow related to, or maybe this is bleeding somehow, or wait, where does this come from? And is it always the same? No, it's not the same. I think it comes from it's just some trash data. So probably the I may be forgetting to put a null terminator or something. So buffer length equals 0, like this. Yep, this I think this fixed it. I wasn't terminating the string. Yeah, this works, but this is probably nicer. So I think that wasn't working because I was because my reverse function did not terminate the string with a null terminator, so the data would just basically I would get some data from an older string or something. And let me see if we can somehow do it in place, like without if let's say if we do it like this, we just have to make sure the so we will pre-allocate the buffer, and just like before, so we will reuse the existing buffer, so we don't have to malloc every single time like this. So void this. Okay. If if length is greater than buff size, realloc. So we reallocate the reverse buffer, and with the length. Okay, reverse this pointer. We reassign this pointer, and then we can ignore this return value. So reverse. We reverse the line to rev like this, and we do not need to call malloc, but instead we just write this to destination tst, and we do not need to return like this. Segmentation fault, great. And why? Wait. Buff size equals 0. Double free detected in tcache 2. Okay, we don't need to free it. Okay. Yeah, it seems to work. So let me once again go over this implementation. We need stdio for standard input output, so reading a line from standard input. Then stdlib for realloc. And we should probably free at the end, right? So free line, free reverse line. Okay. And so this is a line of input. This is a buffer for the reversed line, and the length is the size of the buffer allocated by getLine, and red is number of red bytes, and buff size is the last allocated size of the reverse string buffer. And then we iterate over the standard input with a while loop, and if the existing allocated buffer is smaller than the length allocated by getLine, we reallocate it to make it bigger, so we grow the buffer. Then if the line ends with a new line, we ignore the new line. So this is basically, since C strings end with a 0 byte, if we set a byte to 0, we can just make the C ignore it, and then we reverse every line and store it in the reverse buffer, and then we print a line and append a new line at the end. Then at the end we free the allocated buffers for line and reverse line, because even though they will be freed anyway when the program exits, because this is a good practice, I guess. And then in this reverse function, we first calculate the length of a string, and we calculate the length of a string using string length, and then we basically iterate from 1 to the end. Because we're getting the length, and that length is going to include, and we get the length, and if you want to get the last character of a string, we need to use its length minus 1. So we start from 1, and we iterate up to length, and then we end up at 0. Yeah, basically. But it's basically like this. And then at the end of a destination string, we need to put a 0 so that it doesn't bleed data. Okay, great. Yeah, I'm going to call it done. Okay. And we can go to section 110. The variables in main, such as line, longest, etc., are private or local to main. Because they are declared within main, no other function can have direct access to them. The same is true of the variables in other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a function comes into existence only when the function is called, and disappears when the function is exited. This is why such variables are usually known as automatic variables, following terminology in other languages. We will use the term automatic henceforth to refer to these local variables. Chapter 4 discusses the static storage class, in which local variables do retain their values between calls. Because automatic variables come and go with function invocation, they do not return their values from one call to the next and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables that are external to all functions, that is, variables that can be accessed by name by any function. This mechanism is rather like Fortran common or Pascal variables declared in the outermost block. Because external variables are globally accessible, they can be used instead of argument lists to communicate data between functions. Great. Furthermore, because external variables remain in existence permanently, rather than appearing and disappearing as functions are called and exited, they return their values even after the functions that set them have returned. An external variable must be defined exactly once outside of any function. This sets aside storage for it. The variable must also be declared in each function that wants to access it. This states the type of the variable. The declaration may be an explicit extern statement or may be implicit from context. To make the discussion concrete, let us rewrite the longest line program of line, longest and max as external variables. This requires changing the calls, declarations, and bodies of all three functions. Okay, I'm going to put it on the left. And okay, so this is going to be NCC, so we can copy from video 0 we can copy the clunky file to this ANSI directory, and we can copy the make file to the ANSI directory, and then we can create a file and call it longest like this. Okay, include stdioh, define max line 1000, int max char line max line, so that would be the current input line. Char longest max line, longest line saved here, and then int get line, void copy. Wow. Print longest input line specialized version. Main int length extern int max extern char longest max equals 0 while length equals get line greater than 0, if length is greater than max, max equals length copy. Wow, this is so cursed. If max is greater than 0, there was a line, printf %s longest, and we don't need a we do not need what was it called? We do not need a new line at the end, because it's going to be, there's going to already be one in the line returned by getLine. Int getLine void int ci extern char line for I equals 0, I is less than max line, max line. Okay, I didn't want max input. Okay, max line -1, and C equals get char is not end of file, and C is not a new line, ++I, and then line of I equals C. Okay. If C was a new line, line of I equals C ++I, line I of I equals null terminator return I. Great. And then copy void copy void. So we copy from the void into the void. That's so scary. Extern char line longest I equals 0 while longest of I equals line of I is not 0 ++I. Okay, let's see if this even compiles. Okay. Well then, let's run it on its own source code. Yeah, this looks legit. It's also very cursed. It's so cursed. Which line was it? Yeah. This is visually the longest line in the file. Okay. Yeah, I'm not even going to walk over the code too much, because it's abusing global variables so much, and it's going to, if you write code like this, it's going to be very difficult to maintain, because it won't be easy to see which variables are set where, and it's going to be a pain in the bottom to debug. So I guess they will probably say something about it, or maybe it was before they realized global variables were bad. The external variables in main, getLine, and copy are defined by the first lines of the example above, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like definitions of local variables, but since they occur outside of functions, the variables are external. Before a function can use an external variable, the name of the variable must be made known to the function. One way to do this is to write an extern declaration in the function. The declaration is the same as before, except for the added keyword extern. In certain circumstances, the extern declaration can be omitted. If the definition of an external variable occurs in the source file before its use in a particular function, then there is no need for an extern declaration in the function. The extern declarations in main, getLine, and copy are thus redundant. In fact, common practice is to place definitions of all external variables at the beginning of a source file and then omit all extern declarations. If a program is in several source files and a variable is defined in file 1 and used in file 2 and file 3, then extern declarations are needed in file 2 and file 3 to connect the occurrences of a variable. The usual practice is to collect extern declarations of variables and functions in a separate file, historically called a header, but is included by include at the front of each source file. The suffix .h is conventional for header names. The functions of a standard library, for example, are declared in headers like stdioh. This topic is discussed at length in Chapter 4 and the library itself in Chapter 7 and Appendix B. Since the specialized versions of getLine and copy have no arguments, logic would suggest that their prototypes at the beginning of a file should be getLine with empty arguments, empty parameters, and copy. But for compatibility with older C programs, the standard takes an empty list as an old style declaration and turns off all argument list checking. The word void must be used for an explicitly empty list. We will discuss this further in Chapter 4. You should note that we are using the words definition and declaration carefully when we refer to external variables in this section. Definition refers to the place where the variable is created for assigned storage. Declaration refers to places where the nature of a variable is stated, but no storage is allocated. By the way, there is a tendency to make everything inside an extern variable because it appears to simplify communications. Argument lists are short and variables are always there when you want them. But external variables are always there even when you don't want them. Relying too heavily on external variables is fraught with peril, since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify. Yep, told ya. The second version of the longest line program is inferior to the first, partly for these reasons, and partly because it destroys the generality of two useful functions by wiring into them the names of the variables we manipulate. At this point, we have covered what might be called the conventional core of C. With this handful of building blocks, it's possible to write useful programs of considerable size, and it would probably be a good idea if we paused long enough to do so. These exercises suggest programs of somewhat greater complexity than the ones earlier in this chapter. Okay, there are several exercises, and We have some 50 minutes left, so I think we could try 120, and this is a program that basically should n be a variable or a symbolic parameter? What was a symbolic parameter again? I think symbols a symbolic parameter again. Okay, I don't think the term symbolic parameter is currently in common use. Okay, well, we can try, and then write a program what? Wow, this is a lot of exercises. You can tell it's an old style book because there is a lot of exercises. Write a program to follow long. Oh wow. Don't forget to handle quoted strings and character constants properly. See comments, do not nest. Write a program to check a C program for rudimentary syntax errors like unbalanced parentheses, brackets, and braces. Here, you know what? I mean, we are at chapter 1, and the exercises are like syntax checker for C. Boy. Write a program detab. Okay, I'm going to, I have to do all those exercises. But this is a lot of code to write. Write a program detab that replaces tabs in the input with the proper number of blanks to space to the next tab stop. Okay, so what is a tab stop again? I mean, this is something a boomer would type. So let's say I'm going to be using modern C, I guess. So I'm not going to put that in the unsigned directory. But anyway, let's say just for, okay. Just as an example, a tab stop would be this. And the okay, so let's see what the tab stop is in this system. So cut yeah, so it seems that the tab stop on this system is 4 characters. So the first tab stop would be like 5. So we can, so let's say we are at column 10 and we add a tab stop. Okay, yeah, that seems to make sense. Okay. So yes, we're going to need standard IO. Oh boy. And we are going to be iterating over the this standard input, but we don't really need the buffer. We just need to know where in the line we are. Okay, so let's say int I is going to be the current column in line. Okay. Well. Okay, yep. Int I is going to be a current column in line in C, like this. So we iterate over each character in the input, like so. No, not get C, get char. It's not end of file. Put char C. Okay, so this is just going to return this is just going to return the, this is just going to print the input as same as it was entered, right? So make detab with input of its own source code, like so. Okay, yes. And then you can say if C is a new line, then we reset I to 0, right? Plus I, okay, like so. Yep. So if C is a tab, right? We do not define tab size 4. Okay. So if C is a tab, then we calculate the distance from the next tab stop, like so. Okay, so for example, how do we get from 2 to 4? So I guess if tab is Okay, equals I guess position of next tab stop. Okay. And I equals 0. So if we encounter a tab, so next tab, I guess it would be something like I plus tab size, and then we calculate the modulus minus and next tab equals next tab minus next tab divided by tab size, like this. It doesn't make sense. So we want to make sure it is. We want to make sure that we calculate. So let's say we start at 0. You encounter a tabulator, and then you know that the next tab will be at the tab size, and then you may want to remove some of these. You want to remove characters that are beyond the tab size, right? So let's say we're at 0. This is 0 is going to be, no, who am I kidding? This is never going to be 0. Or maybe there's some maybe there is some more magic, right? So hang on, this is my alarm clock. I honestly don't know if I should finish this. I think this can take some more time, and I'm not going to finish it in this screencast. So I'll see you tomorrow, and there is a long list of exercises, so I guess we will be doing them until the end of the week. And yep, I hope you learned something. If you have, please like and subscribe. It helps me. It gives me a lot of encouragement, and maybe in the future I could do this like on a regular basis. And If you did not enjoy it, you can tell me in the comments. This also helps, I guess. And well, I'll see you in the next video.